Welcome everyone. I am Pierre-François de Plaen, and today I will present our last work, Contrastive Learning for Multi-Object Tracking with Transformers. Inspired by recent advances in natural language processing, the detection transformer models object detection as a translation task going from image features to object-level representations. This approach has a global understanding of the scene thanks to the cross-attention layers. It replaced anchor boxes with a set of learnable object queries, and the method doesn't make duplicate predictions since it learns to agree between the predictions through self-attention layers and loss that includes bipartite matching. This simple yet very effective approach inspired us to develop a lightweight extension of DETR to the multi-object tracking task. In this setup, the model must not only detect objects but also associate instances between frames. We therefore ask ourselves if the object-level representations from DETR encode instance-level features that could be useful for re-identification. The figure on the right shows predictions from DETR on a multi-object tracking dataset. Every color symbol pair represents a different instance over the course of the video. We can see that those representations are not sufficient for object re-identification, since the method is trained to regress bounding boxes and predict classes. Starting from DETR, we add projection head to predict so-called tracking embeddings in which we will encode instance-level features. Those representations are trained with a supervised contrastive loss, which is then averaged over the set of positive pairs for each instance in the mini-batch. More specifically, the positives are objects in the mini-batch that correspond to the same ground truth instance, and the negatives are all the other objects in the mini-batch. Let's now see how we can build such a mini-batch. Multi-object tracking datasets, such as the Berkeley Deep Drive dataset, usually consist of multiple videos. In object detection, frames are sampled uniformly from the dataset. This provides a high diversity of scenes, but if we consider one query object, the probability of sampling other positive pairs is close to zero, while the set of negative examples is quite diverse. However, this is not suitable for the contrastive loss since we need positive pairs. Another approach from multi-object tracking is to sample consecutive frames from one video. This approach leads to a higher probability of sampling many positive examples, but with a very low variety of positive examples, as well as a low variety in the negatives since consecutive frames are sampled. We instead suggest a trade-off in which we first sample multiple videos, here 2 videos, and then, for each of these videos, sample uniformly frames from the video, here 3 frames per video. Our approach leads to a higher diversity in the sampled positive examples, as well as a high diversity in the negatives. Furthermore, since we sample from multiple videos, the scene diversity is preserved, thereby allowing not to compromise on the object detection performance. At inference time, tracking embeddings from the previous frames are saved into a memory bank. Every new prediction is then compared with embeddings from the memory bank by computing the cosine similarity. When multiple embeddings from the same instance are stored into the memory, the maximum cosine similarity is kept. We also add new instance entries to detect objects entering the scene. Those instances are given a fixed similarity score, here a score of 0.5. The global cosine similarity of the matching is then maximized with bipartite matching, which is for example computed with the Hungarian algorithm. This assignment method is computed online frame by frame and is therefore suitable for applications such as autonomous driving. Finally, we introduce a pre-training scheme that exploits the size and diversity of object detection datasets. Since those datasets don't contain instance IDs, we take inspiration from self-supervised learning and take 2 augmentations of every image in the mini-batch. We can now define correspondences between the objects from the 2 augmented views of every image and train the method with an instance-level contrastive loss. Our training strategy, along with the pre-training on detection, allows to learn robust representations even under adverse weather conditions. In this example, we have a difficult night video in which the method is able to distinguish between 2 similarly looking yellow taxis, while being able to identify hardly visible cars. In the ablation study, we investigate the influence of sampling more frames or more different videos and show that we need many positive pairs while sampling from multiple videos. We further analyze the importance of every component by running an ablation study on all the features. This ablation study shows that the contrastive pre-training on detection further boosts performance even on large-scale datasets such as BDD. Let's now take a look at a few qualitative examples. In this nighttime video, the model is able to correctly detect most of the cars and doesn't make many ID switches. Here is another video demonstrating the performance of the method. The model again shows high robustness even under occlusions and difficult weather conditions. We evaluate our method on the MOT17 and Berkeley Deep Drive datasets. Our multitask learning approach, along with a carefully designed sampling strategy, establishes a new state-of-the-art on the mMOTA metric on the Berkeley Deep Drive dataset. This metric emphasizes detection performance. This result therefore highlights the importance of jointly learning detection and association. Results on the MOT17 dataset are also provided in the paper. Future work could investigate adding trajectory prediction or temporal understanding to the architecture. We hope this simple view of the task will inspire researchers in the field. Thank you very much for your attention. Don't hesitate to ask questions at the poster session from WAGV or by email.